This Mathcast will walk you through section 12.1, where your students will learn to write, interpret, and manipulate Taylor polynomials and Taylor series. All of Chapter 12 is devoted to Taylor polynomials and Taylor series. In section 12.1, which is the longest section in this chapter, your students will learn to use derivatives to write Taylor polynomials, and they will thereby discover the general form of a Taylor series, and then shortcuts to write Taylor polynomials and Taylor series through deriving, integrating, or substituting into known series. In section 12.2, they will explore the interval of convergence for Taylor series. And section 12.3 will investigate ways to bound the error of a Taylor polynomial. And finally, section 12.4 will wrap up the chapter and the text by using Taylor series to demonstrate that L'Hopital's rule holds true. Before we start walking through section 12.1, let's examine some of the math notes that are coming up later in this section and this chapter as a way to get a sense of the goals of this section. By the end of the first two lessons of this section, your students will discover and be able to formally define the general form of Taylor polynomials that are centered at 0. And they'll be able to use those polynomials to approximate values on functions and to discuss the error of those approximations. Also, by the end of the third lesson in this section, your students will adjust that general definition of Taylor polynomials centered at 0 towards Taylor polynomials that are centered at other values as well. And by the end of lesson 12.1.4, your students will be writing and analyzing Taylor series as well as polynomials. Now, throughout this section, your students will be learning and memorizing Maclaurin series for some common parent functions, such as sin x, cosine x, and e to the x, which are first introduced in lesson 12.1.2, and then later 1 over 1 minus x, which will be the focus of the next section, 12.2. The first problem in lesson 12.1.1 is written to create a sense of wonder. Your students will be asked to graph a 9th degree polynomial that they will quickly discover resembles a sine wave, at least near the origin. They will then play around with extending the terms of the polynomial and watching what that does to the graph of the curve. Give teams no more than 10 minutes to complete this problem and then pull the class together to discuss what they observed. One good way to share ideas is with a give one, get one study team strategy. This is a quick way for teams to share ideas. What you do is you give each student an index card and have students number the cards 1 through 6. On their cards, they will work with their teams to brainstorm 3 neat ideas that they discussed during this problem, 12-1. Everyone in their team will write those 3 ideas on their cards. And then students will get up and wander around the room, pairing up with different people from different teams and giving one of their ideas to another person who will write it on their card and getting a new idea in exchange, and they'll write it on their own. Once the card is full, the students will return to their seats at their tables and discuss the new ideas with their original team. You could do that, or you could conduct a whole class discussion where students share what interesting ideas they just learned, and of course naming the student who shared it with them, giving credit to that person. The next 4 problems involve a diabolical teacher who challenges her class to use clues to name or to describe a set of mystery functions. Be aware that these mystery function problems will recur throughout this chapter, and it starts right here in problems 12-2 through 12-5. Now, the goals of this first set of mystery functions in lesson 12.1.1 is to guide teams to work together towards writing Taylor polynomials without using an algorithm, so that ultimately, by the time they learn this algorithm, which is at the end of this lesson, they can explain why it makes sense. Now, in this lesson, they're going to be challenged to write the equation of mystery polynomials that are centered about x equals 0. That's what they do in problem 12-2, where they find a way to write a 3rd degree polynomial, given clues about its first 3 derivatives and its value at x equals 0. Teams will probably use a bit of guess and check to write this equation, and that check part is very important. So as you circulate, be sure to ask teams to show you a way to verify that the equation they wrote is correct. And then in problem 12-3, they're going to take it a step further. In this problem, the mystery polynomial is a fourth degree polynomial centered at 0, and they're asked to use it to estimate a specific value of another function that it models, but they want to know that value at x equals 1/2. So as you circulate, discuss with teams the pros and cons of using a fourth degree polynomial to approximate a value versus a tangent line, which is a first degree polynomial, and they've been using tangent lines throughout this course. Now, there are quite a few more mystery function problems in this lesson and in this chapter. So for the sake of consistency, you might want to establish a study team strategy that you could use for all of them. For example, you could use the teammates consult strategy. That's the one where the teacher starts the problem by giving students quiet, individual think time before permitting the group to discuss or execute strategies or even to put their ideas into writing. With the teammates consult, pencils and calculators are put away and students think about the problem quietly, and then without writing anything down, the teams discuss their plans of attack after they've had that quiet time to think. And then the teacher circulates and listens to these conversations, and based on what you hear, you will give teams the go-ahead to pick up their pencils and put their thoughts into writing. This strategy helps to include more students in the planning part of teamwork and promotes discourse about a topic that could otherwise feel very mechanical. Problem 12-5 guides students towards abstractly writing the general formula for any Taylor polynomial centered at x equals 0. It starts with a first degree tangent line, then a second degree polynomial, and a third, and students are to look for patterns and ultimately find the general form of an nth degree polynomial approximation of a function f. Now, of course, this can be very tricky, especially the part where students should be recognizing the pattern in the denominator includes a series of factorials. Some students might not think about the factorial operation because it has not been used that often in this course. So as you circulate, if you notice a team is struggling to make this connection, have a few pocket questions ready to use. For example, you could direct a team to examine the 6 in the denominator of the third degree term and ask them to explain how they found that 6, which they found by multiplying the exponents of all the previous terms. Then ask them to find the coefficient of the fourth degree term the same way. And this could lead to a discussion of the factorial operation. Another good pocket question would be to have teams look back to the opening problem of this lesson, problem 12-1, where they were given a polynomial approximation of sine x. Of course, this polynomial has factorials in the denominator, so that could trigger the idea to investigate whether the general form of these polynomials would have factorials as well. Now that students have learned how to write a Taylor polynomial that is centered at 0, lesson 12.1.2 will have them find the Taylor polynomials for some common functions, such as cosine x, sine x, and e to the x. Now in the first problem, 12-16, teams will work through the long, tedious process of calculating the first 8 derivatives of cosine x and evaluating them into the general form of an nth degree polynomial approximation of a function centered at 0. They found this form at the end of the previous lesson in problem 12-5. They're going to write this polynomial in both expanded and sigma form. And they will even use it to calculate the error of an 8th degree Taylor polynomial approximation of cosine x at various values of x. Now be aware that they will be calculating the actual error, which they're going to need their calculators to do. So part D is a pre-problem for section 12.3, where your students will learn to bound error when that error cannot be determined with certainty. Now on to sine x. Problem 12-17 suggests 2 different methods to find a 7th degree Taylor polynomial for sine x centered at 0. Method 1 involves using the same process as the previous problem. Students will find a long list of derivatives of sine x and their values at 0, and then evaluate those into the general formula for an nth degree polynomial approximation. And method 2 involves using the fact that the derivative of cosine is negative sine, so students will use the power rule to derive the Taylor polynomial for cosine x, which they found in the previous problem, and then negate the result. Now, teams do not need to do both methods. Instead, they should review each method and then choose their favorite. So, since teams are not doing both methods, be sure to give teams that chose different strategies an opportunity to share their work with the other side. This could be accomplished with a team-to-team peer edit, where teams that use different strategies are paired up by the teacher, and then those team members swap papers and read through the work of the other team, and then return the papers with comments, questions, or suggestions. In problem 12-18, your students will convert e to the x into a 7th degree Taylor polynomial and compare its graph to the actual graph of e to the x. Then they're going to use their calculator to find an interval in which e to the x and its 7th degree polynomial approximation differ by less than 0.05 units. Now be aware that your students will be computing actual error in this problem, and they're going to need a calculator to do that. But later in section 12.3, they're going to learn how to bound error, which will not require them to use a calculator at all. Lesson 12.1.3 will transition away from Taylor polynomials that are centered at 0 and towards Taylor polynomials that are centered at other values of x. Problem 12-28 gives an example of such a polynomial. And then 12-29 presents a new mystery function challenge, where your teams will write a 3rd degree polynomial given clues about its first 3 derivatives and its value at x equals 2, not x equals 0. Part B says to describe your strategy and be prepared to share it with the class. This can be done with reciprocal teaching, where you pair up students from different teams and then they take turns with their partner explaining what they did, teaching the other student as though that student was absent during that lesson. In problem 12-30, teams will write 1st, 2nd, 3rd, and 4th degree Taylor polynomials for ln x centered at x equals 1. Be aware that this problem will be referred to in the next lesson, so warn your students to record their answers to this problem neatly and in a way that they can reference later. And in problem 12-31, students will write a 5th degree Taylor polynomial centered at x equals 4 for y equals the square root of x. They will use this polynomial to approximate the square root of 5. They will find that the error of their approximation is very small, which is a marvelous thing. So as you circulate, use the pocket question, what other ways can you approximate the square root of 5 without a calculator? To which students might recall Newton's method, which was introduced in section 4.5 and involves many more tedious steps to achieve this level of accuracy. In the first problem of lesson 12.1.4, problem 12-39, Taylor series will be introduced and defined as a Taylor polynomial with infinitely many terms. Also in this problem, the term Maclaurin series is introduced. Now your students will investigate in task 1 how increasing the number of terms of a Taylor polynomial for, say, cosine x will make its graph look more and more like the function it is approximating. This, of course, is likely to lead to a common overgeneralization in task 2, as many students are likely to predict that as the number of terms of the polynomial approaches infinity, then the polynomial will eventually become the function everywhere. Now, this prediction will be disproved, or rather qualified, in section 12.2 when your students study intervals of convergence of Taylor series. So, knowing that that is coming up in a couple of days, it would be a good idea to memorialize this incorrect conjecture by having each team write their predictions for task 2 on a post-it note and keep those post-its hanging in the room and ready to be revised during lesson 12.2.1. Problem 12-40 is an important problem that focuses on notation. It demonstrates 2 different ways to represent a 7th degree Taylor polynomial for e to the x, sigma form and expanded form. And students are challenged to rewrite or to adjust the sigma and expanded notation in a way that would convert these Taylor polynomials into Taylor series. And then in problem 12-41, students will demonstrate how the expanded form of the Taylor series for e to the x can be used to confirm that the derivative of e to the x is e to the x, and the antiderivative of e to the x is e to the x plus a constant. Problem 12-42 is the one that refers back to problem 12-30 from the previous lesson. In that problem, your students found the Taylor polynomial for ln x about x equals 1. And in this one, they're going to rewrite it as a Taylor series. Now be aware that technically, the Taylor series for ln x has a restricted interval of convergence, but we will hold off on a discussion about intervals of convergence for Taylor series for another 2 lessons. The first problem of lesson 12.1.5, problem 12-48, has students add a general term to the first 4 terms of the Taylor polynomials centered at 0 for cosine x, sine x, and e to the x to create a Maclaurin series for each. Now, your students found and have been working with the polynomial forms of each of these series since lesson 12.1.2. So if you want your students to memorize these series, now is a reasonable time to expect them to do so. The rest of lesson 12.1.5 introduces substitution as a way to quickly write the Maclaurin series for some functions. For example, in part A, students can substitute 2x into the series for cosine x to find a new series for cosine 2x. And the same can be done for cosine of x squared in part B. Now, as you circulate, challenge teams to justify that the substitution method works in part A and B. For example, in part A, your students could find the value of the first 6 derivatives of cosine 2x at x equals 0 to discover that these derivatives do indeed match the constants in the numerator of the coefficients in the series that they found using substitution. They could also use their calculators to sketch the first few terms of the series for y equals cosine 2x on the same set of axes as y equals 2x itself to find it does indeed have a good fit. But for part B, the derivatives of cosine of x squared all equal 0, which does not match the coefficients of the numerators of the series that they found using substitution. So consequently, graphing and comparing is the best way to verify that this series is correct. Problem 12-50 allows teams to practice writing Maclaurin series using the substitution technique, while problem 12-51 focuses on how Taylor polynomials can be used to approximate the value of definite integrals, such as the integral of e to the x squared on 0 to 1. Your students will discover that finding the antiderivative of a polynomial is a lot easier than finding an antiderivative of a composite function such as e to the x squared. The result will not be exact, but it will be a close approximation nonetheless. And in that spirit, the remaining problems in this lesson and this section demonstrate ways that Taylor and Maclaurin series can be used to simplify the application of other tools of calculus, such as evaluating these 2 famous limits. So, if time remains at the end of class, have students do a scavenger hunt through their texts to find other ways to prove that the limit as x goes to 0 of sine x over x is 1, and the limit as x goes to 0 of 1 minus cosine x over x is 0. For your reference, back in Chapter 2, students evaluated these limits the first time by zooming in on their calculators and recognizing the relationship between the linearization of the numerator and the linearization of the denominator at x equals 0. There was also a math note in Chapter 2 where students were guided through a trig proof using the squeeze theorem of these 2 limits. And then in Chapter 3, they evaluated these limits by interpreting them as the definition of the derivative, the one where x goes to a. Later in Chapter 5, they evaluated these limits using L'Hopital's rule. And here in Chapter 12, they're using Maclaurin series to simplify and evaluate these limits. This is all in the spirit of mixed-spaced practice. So this concludes our walkthrough of section 12.1 on Taylor polynomials and Taylor series.